All right. Hello, everyone. My name is Shelley Welton. I am a professor over at the law school and here with the Kleinman Center for Energy Policy. And I have the pleasure of getting to moderate today's panel on Towards Environmentally Sustainable AI. So this is the third workshop in a year-long series of workshops on AI and climate change that are organized by the Penn Program on Regulation. And the goal of the series is to understand better the connection between two of the most pressing developments happening today, artificial intelligence and climate change, while also bringing together students and faculty and staff from across Penn's different schools who share these interests. We have 3 more workshops coming up in the spring, and there's going to be announcements about those after the holidays. The series is made possible in part by funding from the Provost Environmental Innovations Initiative, and other co-sponsors include the Kleinman Center for Energy Policy, who's been kindly hosting this workshop series, the Center for Technology Innovation and Competition, the Warren Center for Network and Data Sciences, and the Wharton Climate Center. So our previous workshops in this series have focused on the ways in which AI can help us to understand and combat climate change. And today we look at a different kind of connection between AI and climate change, AI's carbon footprint and the challenge of making AI computing more energy efficient. So we're pleased to have with us 2 faculty experts on these topics, Professors Deep Jariwala and Benjamin Lee, who are going to share their research on the environmental impacts of artificial intelligence and talk about the ways that the field of AI can move forward in more environmentally sustainable manners. Before I turn the floor over to our speakers, just a couple of housekeeping items. First, today's workshop is being recorded, and the recording will be posted on the Penn Program on Regulation's YouTube channel. And then after about a 40-minute presentation by Professors Jariwala and Lee, we look forward to hearing from you, getting your questions. So during the Q&A session, just raise your hand if you want to speak, and we will have a couple of microphones circulating. So wait for a microphone before you ask your question, please. Without further ado, let me introduce our speakers. First, we have Deep Jariwala, who's an associate professor of electrical and systems engineering and the Peter and Suzanne Armstrong Distinguished Scholar at Penn Engineering. He's an expert in nano and atomic scale devices that have potential applications in information technology and renewable energy, among other fields. Professor Jariwala leads the Device Research and Engineering Laboratory in the Singh Center for Nanotechnology at Penn. And his research has earned numerous recognitions, including the Photonics Society Young Investigator Award and Nanotechnology Council Young Investigator Award from the Institute of Electrical and Electronics Engineers. And in 2002, he was a recipient of a Sloan Foundation Research Fellowship and the Bell Labs Prize. And second, we have Professor Benjamin Lee, who is a professor of electrical and systems engineering and professor of computer and information science at Penn. Recently, he was also a visiting research scientist with the Fundamental AI Research Team at Meta AI. Professor Lee's research focuses on computer architecture, energy efficiency, and security. And he is also an award-winning scholar, previously receiving the National Science Foundation's Computing Innovation Fellowship, an NSF Career Award, and Google Faculty Research Award. And he's a distinguished member of the Association of Computing Machinery, among many other recognitions. They made my job hard only by being so decorated. Okay, so without further ado, I'm delighted to turn the floor over to Professor Jariwala to get us started.
All right, great. Can everybody hear me all right? All right, wonderful. Well, thank you, Shelley, for the very kind introduction and for Andy and others for inviting us over here. This is certainly a unique opportunity for me. I don't speak that often to this such intellectually diverse audience, so this would be a great chance to showcase some of the things that are happening in the world of AI hardware and where things are going and how our research is connected to it. So as Shelley mentioned, I'll be talking about environmentally sustainable AI, mostly hardware and its challenges. And so to get started, let me put up a couple of news pieces that have been circulating recently. It's actually even more appropriate today. Has anybody seen these type of news articles appearing about, I would say, a month or two ago, not September, right? So about a month and a half ago. Microsoft had posted a job announcement looking for program managers for nuclear power reactors. Right now, this headline in particular would also be very appropriate today, given all the chaos that is happening at OpenAI, metaphorically. But still, this is actually quite a startling sort of job announcement that Microsoft put out. Why the heck would Microsoft need nuclear power reactor managers? It's because there are data centers that are basically going to be going gangbusters on AI, are going to be consume so much energy that they would need their own power sources. So this is where the world of AI is heading. Large AI companies or large companies that serve the world's need for AI will need to also produce their own power. So this is not a distant reality. It is happening as we speak. Right. So another headline, or these kind of headlines actually appear every week, which is AI is booming and helping planet Earth burn faster. It's not false. There's nothing false in these headlines. Some of it is, of course, driven by hysteria or trying to get people to pay attention to things. But there are legitimate scientific and technological reasons behind this, which is what I would like to highlight. That the rise in AI or rise in data-heavy computing is certainly impacting our energy consumption, and as a consequence, global warming and climate change are quite adversely, right? And so these things are all connected, certainly. Okay, so I would like to mention this in the beginning itself, that AI is packaged or repackaged by the community or the world or the press in different ways as time progresses. But very rudimentary forms of AI are basically any big data operation. And this has been going on since the advent of search or Google search. So when these big internet companies started and they started providing applications which consume vast amounts of data on the internet, you could call them rudimentary forms of AI. It has taken a whole new word and meaning now with the launch of ChatGPT and other image recognition, speech recognition applications, and so on. Okay, so let me move to a little bit more technical part over here. I promise there won't be too many technical slides, barely 3 or 4, but since I understand this is a very general audience. But we like to talk a lot about computing hardware, because computing hardware is certainly the basis behind AI. The algorithms and the theory behind AI, which is machine learning, deep learning, and other of this neural network type softwares, this has been around for quite a while, decades, I would say. It's the advances in hardware and how good hardware has become over the years. It's leading us to implement these things into software, and they are now becoming a reality on the grand scale servers that the companies are hosting. But if you consider classical computing as a whole, which is the computer that each one of us is holding in our hands or in our wristwatches or even our computers or the laptop computers, they have their own challenges happening for over many years. One of those big challenges, basically, the steady state power consumption is sort of increasing, right? And this has been happening for about a decade and a half now, despite all the advances that have happened in making tinier and tinier devices. The second problem, which is on the right-hand side of the screen, is, I would say, more of a post-iPhone era problem, right? And so I call this post-iPhone era problem because once we have devices which is not just one desktop computer or one laptop computer, but 5 computers now, one in our wrist, one cell phone, one in our iPads, and so on, you start generating enormous amounts of data. And so as a society, we have taken started to take a paradigm shift since the advent of smart devices and smartphones to go more from a arithmetic logic-centric computing, or computing that requires a lot of addition, subtraction, multiplication operations, to something that is more data-centric, so more data-heavy computing. And this data-heavy computing inherently relies more on memory devices. So memory devices from which the computer will read the data, try to infer. For example, if you are searching for an image or trying to infer an image. So image recognition, speech recognition, text recognition, these things are extremely data heavy. And so what happens in traditional computing architectures is that because there is always an exchange of information between the memory and the processor, so to speak, if your computing becomes extremely data heavy, then these highways connecting the memory units to the processor, which is arithmetic logic units, are jammed all the time. And this increases both the time taken to compute and therefore the energy efficiency to compute goes down. This inherently then leads to more heating up of the computers, and therefore we have the power consumption issue to some extent. Okay, this latency or traffic jam, so to speak, between the logic units and the memory units is very well known. It's known as the memory wall. In technical terms, it's known as the von Neumann bottleneck. We can discuss more about it during questions if you'd like. But let me go further and to try to ask another question, that why is power consumption a challenge? And before I sort of ask that question, let me ask everybody who's not from the engineering school, do you know where this is located? Anybody knows? And not from the engineering school. Okay, this is located in the Moore building. It's one of the remaining pieces of the world's first general purpose computer, the ENIAC. As many of you know, the ENIAC was made or invented at Penn in our department. And so this is still there. It's of course a museum relic now. Various parts of ENIAC have been shipped to various computer history museums across the world. But ENIAC was funded by the Department of Defense back then to actually calculate ballistic trajectories. So it has its origins from for calculating trajectories of projectiles, but then it led to the full big computer revolution. So why am I talking about ENIAC? Because ENIAC used to occupy the entire basement of Moore building at the time, and turning it on would basically require consuming power that entire university city would consume today. Okay, so that was the days of the ancient computers, so to speak, which were extremely power hungry, requiring powering them would require energy that modern cities or portions of cities would consume. So here's another graph that basically puts all of this into perspective. If you consider ENIAC, every amount of energy required per useful computation was about hundreds of joules. Okay, and then there is a large gap both on the y-axis and x-axis. In that gap is where the semiconductor revolution started, right? And people figured out that ENIAC, which was built with vacuum tubes were the driving devices of ENIAC, and we went to a hardware which was driven by semiconductors, or in other words, tiny chips or crystals of materials on which electrons will shuttle around. And then there was the birth of the IBM PC and so on and so forth. What you're seeing over there is, as time progresses on the x-axis, on y-axis, exponential reduction in the energy consumed per useful computation. Okay, so over the past many decades, we have made tremendous advances in pushing semiconductor technology to the point that we are now doing computations in the latest NVIDIA GPUs and Google TPUs at 1 picojoules. Okay, so each valuable computation requires about a picojoule, which is 10 to the power minus 12 joules. Such is the level of energy efficiency we have reached. But you can also see from this graph that there is a line called the CMOS limit. CMOS stands for complementary metal oxide semiconductor technology. This is our technology based out of silicon, right? All the computing that we do in the world today, or 99.9% of the computing that we do in the world today, is based out of silicon. That line, that black line over there, that's the limit of silicon-based technology out there. You'll see we are not very far away from that limit. Right, so that's where we are reaching. So if computing is becoming so much more efficient with progressing time, why do we care about AI and energy consumption? Why are these AI companies putting up their own or thinking about putting up their own energy sources? The answer to this lies in various other studies, and this is what I'm going to highlight for the next couple of slides. There was a popular article published in Nature in about 2018 about forecasting energy consumption by all of ICT industries. ICT is a very popular term or acronym used for information communications technologies, right? So everything that comprises of our everyday computing as well as communication, which means cell phones and associated the internet connected devices, so to speak. The prediction was that by 2030, which is not too far away, 21% of all global electricity consumption will be required by ICT applications. 21% is not a small number. Okay. Now, these numbers are always a little bit under debate. There are actually people do much more detailed studies on those numbers. My esteemed colleague Ben Lee will actually tell you much more concrete and in-depth numbers of these things than myself. But let me point you to another chart, which is on the right-hand side again. And this chart was produced by the Semiconductor Research Corporation. The Semiconductor Research Corporation is a consortium of all major hardware companies that you may have heard of. And they put together this graph showing what is the energy consumed by ICT devices as a function of time, which is years. And the computing and communication devices are put on those graphs. And then various studies are those yellow dots. And the world's energy production is that yellow line up top. Now, once again, you'll see that the y-axis is the logarithmic scale. And so you would see that the world's energy production doesn't rise very fast. Okay, we do not. The world's energy production does not increase exponentially unless we come up with a transformative new energy source like fusion or some other exotic energy source that we have not found yet. That is not going to dramatically change. On the other hand, if you look at the computing, the energy consumed by computing and communications devices, they are on a much steeper slope. This means come 2040 or so, the total amount of energy required for computing and communications devices will exceed global energy production, entire globe's energy production. This is clearly unsustainable, right? We need energy for other things like lighting, heating. Even if you were to go all electric cars, you need energy to charge up those electric cars. Where are you going to get that from? Okay, so that's where we stand. But certainly we cannot cross the yellow line. So what is going to happen is a market-driven scenario. And the market-driven scenario is the following, which is our ability as a species, as a world, as a humanity, will be limited to some number in terms of amount of computation we can do. And this number, again, varies, depends on study to study, but this is the perfectly envisioned scenario. The number quoted in this study is about 1,000 ZIPS. So what ZIPS means? It's a zeta input-output operations per second, which means 10 to the power 21 input-output operations per second is what we do today, approximately 1 ZIPS, around 2020 or so. That's the amount of computing we do as a society, as a whole world today. We are expected to grow about 1,000 times more and maybe flatten out over there unless we find a transformative new energy source, or we find a transformative new way to do computing. That is what can push us into those blue squares. Blue squares are regions where you find transformative new ways to do computing in a more energy efficient way. Okay, so there are two solutions out. Find a new transformative energy source, which has to be clean, or find transformative new ways to do computing, which is way more orders of magnitude more energy efficient than it is today. So that is the space I sit in. The second space is what I usually sit in and try to figure out ways to do it. Different people try to think about it differently and have different solutions to it. You can attack it in various different ways. The way I try to attack it is develop materials and devices that maximize the bit operations per watt of power. But this is sort of the central mantra, if you will, of all semiconductor companies, whether hardware or software, is how do you do more and more number of computing operations per watt of power consumed. People like myself think about it in the materials and devices level. People in the circuits and architecture think at the systems level. People in algorithm and software space think in software levels, right? So now there are computing is a complex process. There are various ways to do computing. Well, there are various aspects to computing. There is the logic part. There is the memory part. I'm going to focus on the memory because memory is what is limiting AI today. Okay, so these are graphs taken from a blog. Okay, and again, I don't want to go into too much of details of this graph, but the y-axis is again an exponential scale that is telling you the amount of computing power required to just train one of these algorithms or one of these software architectures. What are these software architectures? Well, there are several architectures mentioned over here. I'm going to focus on the transformer architectures. Any transformer fans here? Okay. Oh, yeah, Ben is a transformer fan. So transformer architectures is what you would probably know as ChatGPT. Okay. OpenAI gets a lot of credit for ChatGPT, but the transformer architecture was developed at Google DeepMind, if I'm not mistaken, or Google AI, I'm sorry. And so the transformer architecture, as you can see, the amount of computing power they require just to train them is rising quite exponentially, these red dots. Compare that to computing power rise of semiconductor hardware, which is Moore's law, as we probably know, or many of us know, and that's that gray line or black line down there. There is a clear mismatch between the two, right? So existing hardware cannot or is inadequate to handle the rise in the amount of computing power required by the software or AI software in particular. Let's put another graph over here that makes even more sense. As I mentioned to you earlier, memory is the bottleneck because all AI algorithms are highly data intensive. So what the software industry or hardware companies have tried to do, especially NVIDIA and everybody who makes GPUs, is to pack more memory as close to the processor as possible. And that is what you would call as the green line, which is AI hardware memory, right? You look at the rise in the amount of AI hardware memory as a function of time with various versions of NVIDIA GPUs or Google TPUs. Compare that to the transformer size, which is again the red dots. You'll again see that we have reached a point of inflection and we are diverging quite a bit. What is there on the y-axis? The y-axis is something called as parameter count. You can consider that as the number of parameters is directly proportional to the amount of memory required for the software or the AI algorithm to operate. And so it is rising also in billions. It's already exceeded 1 trillion, for example, GPT-4, which is the latest version of ChatGPT. So what really is the solution over here? The solution is to densely pack memory with the computer processors. So the next 2 or 3 slides are probably the most technical I'll get to. So if you look at the current generation of microprocessors that's on the left-hand side, the processors and memory, different types of memory, slow memory, fast memory, non-volatile memory, which is basically storage class memory, they are located at different distances from the processor and information is being exchanged on it. This is all laid out laterally. So there are like information highways or wires transporting all this information. Now, the goal or the vision is that instead of having a strip mall parking lot, have a skyscraper and pack everything on vertical floors. Have all the data being stored on vertical floors, and the bottom floors, which we would normally consider parking garages, be your processors or silicon processors that do the computing. It's easier to show it on a slide. It's extremely hard to execute it in terms of making these devices. Okay. So there are many types of memory devices under consideration. I'm not going to go into details of all of them. These are popularly known as back-end of line memory technologies. These are non-volatile memory technologies. That means when you are not operating them, they are not actively consuming power. Therefore, they are called non-volatile. The ones that our group at Penn, along with others, is focusing on are ferroelectric memory technologies. They are basically electrical equivalent of magnets, right? So my colleague Troy Olson and myself, we have been focusing on a novel class of ferroelectric materials that was discovered in 2019. This has some very unique and interesting properties that makes it very suitable for low power memory, and not just low power memory operation, but it is something, this material is amenable to fabrication on top of the silicon microprocessor. So this vertical architecture that I spoke about would be possible with this type of a material. It's already in your smartphone, but not as a memory element, as a filter for your 4G or 5G phones. It's already there in your smartphone if you bought one in the last 2 to 3 years. Again, I won't go into details of devices, but these memory elements operate in differences in resistance states. So we can store at a high resistance state would be, for example, information 0, low resistance state will be in information 1. And so we have developed these type of devices. A particularly interesting aspect of these devices, and I'll show you some pictorial comparisons over here, is if you were to use the type of memory devices we're making, you could do search, computational search, using a very simple circuit architecture shown right here towards the very right of the screen. If you were to try to do a search, which means, for example, you have a string of data you are trying to search in a giant database, using silicon-based hardware or current silicon-based hardware, the circuit would look something like this. We are reducing the complexity of circuits by about an order of magnitude. Instead of 16 transistors, you require like 2 resistors to do this. This simplifies the whole idea of searching, not just makes it faster, but also more compact on the chip, and more importantly, makes it much more energy efficient, which is what we are going towards. So anyways, we've done all this benchmarking and comparison with various other technologies. This was very well recognized by the Bell Labs Prize. As many of you know, Bell Labs was the birthplace of the transistor and the subsequent a revolution in sort of computers and microelectronics. Okay, so last couple of slides, let me talk about another important aspect, which is, can you also do, for example, multiplication with memory devices? This is something that requires a lot of computational power typically. So you can envision multiplying matrices is very, very hard in computing. But if electrically, if you can map the matrices to different types of resistor elements at every node, you can do this. So you would need some kind of analog programmability of memory devices. This is also something we have achieved, so it makes it very promising to then develop brain-like computers. This is one of the holy grails of AI, or people who do AI hardware, is humans or human brains are very perceptive, and we can do certain tasks and certain computations like distinguishing a cat from a dog with very high degrees of energy efficiency. For digital computers to do that is extremely hard. And that's because our brains are analog. They work on analog signals, and they don't have memory units and computing units. They're separate. They're all meshed together in one neuron. So can you build computers that are more like the human brain? And to do that, you would need to have analog programmability of devices, which what we are showing now. Let me point to one last problem and then end over here, is that it seems like memory is the critical bottleneck. And if you were to solve the memory problem, maybe you could solve all of this. But does that sustain with the amount of resources you need to produce the memory devices? Here is a chart again from the Semiconductor Research Corporation decadal plan. The right-hand side shows you the growth in memory that would be required for storing all the data we are producing. There is an upper bound, which is an overestimate, I would say, and then there is a very conservative lower bound. You see what we are going in terms of on y-axis, again, it's zettabytes. It's a very, very large number, and that's again exponentially rising. So if you compare by 2040, and I take a very conservative estimate, say just 10 to the power 24 bits I need to store, and if I take the assumption that 1 bit will require about 1 picogram of silicon to store, I still need about 10 to the power 8 kilograms of silicon wafers. The global production of silicon wafers by 2040 is not going to be at that level. Okay, I'm a metallurgical engineer by training. My undergraduate degree was metallurgical engineering. Producing silicon from sand is probably one of the most carbon unfriendly processes out there. Okay, so if we need to ramp up our silicon production by orders of magnitude just to store all the data that we are producing, oh boy, we're in a lot of trouble. Okay, so with that, I would like to end and summarize that current hardware is reaching its limits in terms of energy efficiency, physical limits. Partly physics, partly materials are limiting us. AI software needs for better, more memory-intensive hardware, and that need will keep rising for the foreseeable future. The energy cost of AI will become unsustainable in about a decade or so, unless energy policies and production for energy changes. At a hardware level, we need new materials, new devices, or novel physics, which will be necessary to sustain the needs of AI. With that, I'd like to end. Thank all the people who have funded our research. Most importantly, I'd like to thank my colleagues and collaborators, Troy Olson and Eric Stack, as well as various others at companies and national labs, and some selected references out there. I'll be happy to take any questions later on.
All right, good afternoon. Thanks so much. Deep, thanks so much for getting us started. A really great introduction to the underlying technology. Delighted to be here. Thanks so much, Shelley, for the introduction earlier. This talk is just to give you a quick sense of where high-performance computing is going. Deep gave you a really great sense of the underlying technology, the memory technologies, the power trends. We spent a lot of time thinking about computer architectures and high-performance data centers. How do you build high-performance microprocessors, memory systems, and how do you deploy them in these massive data centers that Microsoft, Google, Amazon, Meta, all of these companies are building at great scale and at great speed nowadays in response to AI and machine learning. So many of these insights have arisen from characterizations of rapid growth in machine learning models. There has been this data has been analyzed in lots of different contexts and lots of different ways. I particularly like this figure from The Economist, but it's essentially showing how big these models are getting. These models are increasing in size by about 10 times a year. And the difficulty is that we're seeing this exponential growth in computing demand, just as we're seeing a slowing in the exponential growth we have been accustomed to in transistor scaling. So we've been used to getting transistors that are smaller, faster, and more power efficient. We're no longer getting that. We haven't been getting that for about 10 years now. And at this point, we're now seeing rapid exponential growth in the demands for compute. So this is a concern. This is driving at system levels, massive growth in data center capacity. So here we're seeing on the y-axis the number of the amount of energy required by these massive data centers. And these numbers are growing somewhere between 8 to 13% per year. So this is fairly rapid growth. We see companies investing fairly significantly in the amount of facilities and the infrastructure they're building. This massive rollout in data center computing has a fairly local impact on communities that are homes to these data centers. It's interesting to note that there are quite a few data centers being built locally in Virginia, and Northern Virginia in particular is home to many of these data centers, and they're finding that this has become a problem. As these data centers roll out in Northern Virginia, they are stressing the grid. They are requiring new installations of transmission lines. And there are concerns that essentially taxpayers or ratepayers in Virginia are subsidizing data center scale computing, right? It's been projected that Virginia is going to be unable to meet its renewable energy goals because of this massive growth in data center energy consumption. We see this also in Ireland. Ireland is actually home to quite a few data centers, in this case, because of its attractive tax structure. And here again, when we look at recent reports coming out of the utility companies in Ireland, we see that they are projecting massive amounts of data center energy consumed locally on this island, up to 28% by 2031. So these are fairly troubling numbers that have fairly localized impact. You can look at global data center energy consumption, but in fact, we see concentrated growth in particular locations throughout the United States and in Europe. So in this talk, I want to highlight 2 or 3 studies we've done in the context of data center energy consumption. These collaborations, these studies were done in collaboration with Meta, when I spent 2 years collaborating with their AI teams and looking at their data center infrastructure. The first thing to understand about the carbon footprint of computing is that there are 2 components to it. The first is embodied carbon, the carbon that goes into manufacturing your consumer electronics, the carbon footprint associated with semiconductor manufacturing, the fabs. And embodied carbon is most notable in consumer electronics because they don't draw that much power, but they have a lot of electronics deep inside them. So the classic example is your iPhone. And here we see that most of the carbon footprint of your phone is in manufacturing carbon, the integrated circuits, the boards, the frame, the electronics. And the actual power use from your phone is relatively modest. On the other hand, when we think about data center computing, this is where we care about operational carbon, the amount of electricity being used by these data centers and how that electricity is being generated. By some estimates, when we look at the largest data center operators in the United States, we see that in total, they consume more energy than the state of Massachusetts, and they are approaching the numbers we are seeing for New England. So these numbers are fairly large and growing rapidly. When we look a little bit more deeply into the carbon footprint associated with machine learning in particular, we see that there is the operational component, the electricity that's being used for machine learning, but then there's also the embodied component, the cost of manufacturing those really high performance data center servers and deploying them within these massive facilities. We find that in data centers, operational carbon dominates. How do you use your electricity? Where does that electricity come from? That is perhaps the most important decision when you want a carbon-free data center computing. Most players in this space are now focusing on net zero. In practice, what they mean is that they are buying offsets. They are going and buying renewable energy certificates. And as a result, they are able to offset the amount of energy their data centers are using. The experience at Meta has been that with iteratively better optimizations, we're able to improve power efficiency, reduce the power cost of computation by about 20% every 6 months. Now, if you compound this over 2 years, you would say, well, maybe at the end of 2 years, my power has gone from its original value down to 40%. And that's not what we observed, actually. That's not what Meta observed. They found that if you were able to reduce power by 20% every 6 months, in the end, you only get a 30% reduction at the end of 2 years. What happened? The concern is, the hypothesis is that as our systems became more power efficient, we ended up computing more. This is classically known as Jevons paradox. Efficiency breeds greater use. But the question is, how do you estimate this effect? How do you quantify rebound effects? It's extraordinarily difficult under normal circumstances. There's been lots of literature in energy efficient lighting and electric vehicles. It's even harder for hyperscale data centers because the applications and the system settings we're talking about are evolving just so rapidly. Now that we understand how machine learning affects data center energy usage, let's talk a little bit about the solution space. In 2023, we published a paper that talked about the possible solutions for carbon-free data center compute. And much of this requires stepping away from simply connecting your data center to the grid. If you simply connect your data center to the grid, well, then your carbon intensity of that energy is going to be simply whatever mix of energy sources the grid decides to install. You can do better than this, and this is effectively what most data center operators are doing today. They're doing net zero operations. How do they claim net zero? They go to the grid operator, they say, I want to install wind farms, I want to install solar farms, and for those installations, I will have power purchase agreements. So all of that carbon-free energy that's being generated, I will get credit for. And at the end of the year, I will check to make sure that I've received enough credits to offset my data center energy usage. The difficulty with these offsets is that you can look at the end-to-end offset at the end of the year and say, I'm carbon-free, I'm net zero. But still, there will be many hours throughout the year where there simply isn't enough carbon-free energy on the grid, and you're going to have to rely on natural gas or coal or some other more carbon-intensive source of energy. So net zero is a step in the right direction. It's really accelerated a lot of renewable energy installations across the United States, but at the same time, it doesn't really affect the core of the problem on an hourly basis. To really address the core of the issue, we need to do demand response. And many of you who've studied sustainability knows that demand response is really matching your demand for energy against the supply of renewable energy. And we would like to do this in a fine grain on an hourly basis. This is really difficult, especially for data centers, because they don't want to defer their computation. They don't want to reschedule their jobs. in response to the carbon intensity of the grid. They just want to compute. So the question is, how do we incentivize demand response? How do we get data center operators to shift their computational loads based on signals from the grid? Demand response will be incredibly important because when we see the rate at which renewable energy is being installed, by one estimate 7% per year, and we see the rate at which data centers are growing by another estimate 25% per year, we find that there's no way to get to carbon-free compute solely by installing more and more renewable energy. Right? So you can't simply invest your way out of this problem. You have to figure out how to schedule and how to modulate your demand for compute based on when renewable energy is more abundant. So the solution space includes three main strategies. The first is, yes, continue to invest in your renewable energy. The second is install batteries, utility scale batteries that allow you to store carbon-free energy. And the third is carbon-aware scheduling. How do you defer computation and schedule computation to take advantage of times when renewable energy is abundant, like in the middle of the day, and throttle back when renewable energy is scarce, such as the middle of the night. Just some quick headlines with respect to these numbers. When we invest in renewables, yes, renewables get us a good way there. We can go from 0% carbon-free compute to 95% carbon-free compute. But if you want to cover that last 5%, it's going to require 5 times more renewable than you had installed to get to the first 95%. So the diminishing marginal returns, right? You really can't get to carbon-free compute solely through investing in renewables. Batteries have to be part of the solution. Suppose that you install utility scale batteries when renewable energy is abundant. For a number of different data centers, we find that it might be possible to get to carbon-free compute if you allow the data center to compute for 3 hours every day on batteries. That's actually a lot of battery capacity. That's megawatt hours worth of battery capacity. But at the same time, utilities are already building out batteries of this size and spending tens of millions, hundreds of millions of dollars on batteries is still only a fraction of the cost of building the data center itself, right? So these numbers look big, but they're small relative to total data center cost. And then finally, you want the data center to be able to flex up and compute more when renewable energy is abundant. This means buying a lot of servers, extra servers, and turning them on only in the middle of the day when you have lots and lots of renewable energy. This is interesting because if you have lots of these extra servers, they're going to be sitting idle most of the time, waiting for that renewable energy to show up. But when it does, they all come online and you all compute, and they compute more. And the trade-off here is if you deploy more servers, you're going to have more embodied carbon, but you're going to have more flexibility that might lower your operational carbon. So do you come out ahead? That's one of the questions we've been asking. So we developed a framework where we looked at the solution space, tried to figure out how to balance operational and embodied carbon. I'm not going to go through this analysis except to say that you can construct a Pareto frontier and determine how much embodied carbon you need to spend in order to reduce operational carbon. I'll close by saying that we need new strategies for scheduling and managing data center compute. And many of these strategies rely on incentives so that strategic users will modulate the demand for compute. Much of this will require signals from the grid. Can you communicate when energy is carbon intensive, and then ask the data center and its users to reschedule their work in response? This requires understanding the relationship between computational power and computational performance, which real-time workloads can benefit from less compute, which batch workloads can benefit from deferred compute. And finally, we want distributed decision-making. We've been exploring tax and rebate schemes where we tax data center power usage within the data center itself, and then we offer power at other times of day to compensate users and their workloads for participating in those demand response schemes. So in summary, we think it's incredibly important to think about sustainable AI. We're all here because we think that way. We want to sustain exponential growth in computing. We're not ready to throw out the white flag yet. We think that we can continue to sustain this level of compute, but it requires coordinated thinking on renewables, batteries, and servers. And it requires thinking strategically about incentivizing users with their own selfish performance goals and how to get them to use more or less power depending on the carbon intensity of that power. So lots of really interesting questions. I think we're just getting started. I'm really hoping to foster a conversation, maybe find some collaborations in this community. Thanks so much.
Okay, thanks to you both for those fascinating presentations. So start to get your questions together. We've got some microphones getting geared up to come around. I'll take moderator's prerogative just to ask one, which is just really trying to marry what I think about all day with what you all presented on today, right? So as I understand it, a lot of the companies that are leading the way in the AI space are paying attention to climate change voluntarily, right? And really taking a lot of the initiative internally. These net zero pledges aren't legally mandated. So I wanted to ask you both, like, what role do you see for law and policy to drive change in this space, right? Like, is this just, let the innovation happen and law and policy would be a hindrance at this point? Or do you think there are policies that we could adopt that would be productive in pushing forward the kinds of changes we need to see?
Yeah, that's a great question. I think you're absolutely right that big tech is self-policing at this point. They are publishing sustainability reports and selecting the metrics where they can get the biggest visible bang for their dollar. And that's why you're seeing lots of investments in renewable and so on. From a regulatory perspective, I think there is a question about how power is purchased from how renewable energy is purchased from these grids. There is a concern that these big tech companies are consuming so much renewable energy that they're crowding out other industries, or they're distorting the market. And you see this sort of in some of these, like, utility companies in Virginia are saying that they are competing with Google for renewable energy installations because Google wants to get credit for those installations and they're willing to pay for it. And that may affect Dominion Energy's ability to install renewable energy. So whether that's a market issue or a regulatory issue, I think that's an open question. The second point I make about regulatory issues is that I do think it's an exciting time to be in AI right now. So just like regulating AI for safety and security, I think there's a question about when to do it. And I tend to be a little bit more on the side of giving them a little bit more space to run, thinking about energy efficiency, sustainability now, and having those solutions ready for when they're thinking about when they're ready to think about this. Just one last story is that when I was at Meta, everyone was excited about sustainability. We were working on it very hard. And then LLM, large language models came out and everyone shifted over. So I think the mind share has really changed in industry, and we'd like to give them space to explore, but then have these solutions ready when they're ready for it.
Yeah, thanks for the question. I share the same feeling that what Ben conveyed. A large amount of the responsibility is being the big companies or big tech are taking responsibility on themselves. This is also true for chip manufacturers chip manufacturing plants are actually heavy polluters and heavy energy consumers too. And more and more they are adopting practices that require less use of toxic chemicals, more water recycling, installing their own renewable energy sources, and so on. I don't necessarily think that putting in more regulation can help from at least the government or law policy. What could help is not only force, or I wouldn't say force, but encourage the companies to innovate in terms of their own technology and installing renewable energy or more sustainable practices, but policies could be made that encourage them to come up with innovations, even in the renewable energy space. I mean, these are tech companies. A lot of this tech is connected. Solar panels are made out of silicon, and chips are also made out of silicon. It is not hard for the same companies to innovate in both spaces. So I'm sure regulations could be placed that help them innovate on safety. The same holds for batteries, for example. Like a lot of battery technology uses the same kind of processes these days that you would use in semiconductor manufacturing. So why not?
All right, let's open it up. Who has questions? How about over here to start?
In the medium term, let's say 10 to 15 years, what do you see for the role of quantum computing in energy consumption?
I can take that. A lot of people hate me for this, but quantum computing is not real. It's one of those technologies like fusion, which has always been 20 years away. I'm not sure whether it will become real in our lifetime. There are many, many question marks on what quantum computing is good for, what is it useful for. Even if it becomes useful, there are a very specific sets of tasks that quantum is good at doing. There is no chance it replaces classical computing within our lifetimes.
I'll also add that I think quantum computing offers, if it plays out, I think it offers qualitatively new capabilities. For example, people worried about the safety of their encrypted data if quantum computing were to actually arise. Some implementations of quantum computing require extremely low temperatures to operate, and so your compute may end up being more energy efficient, potentially, for an answer that you previously couldn't compute. But at the same time, maybe you have to cool the system down, and that also requires a lot of energy. So there are interesting trade-offs there, should the technology play out.
I just want to follow up on that question quickly and point out that fusion has been slowly coming up to roost. There's been a lot of impressive development, including a break-even point. So that's very promising for these questions. I'd like to focus the question specifically on quantum entanglement. So I understand that there's the question of quantum computing, and I mostly have your agreement that we don't really know what it's good at for. But there's this idea of quantum entanglement that would allow you to transport energy from one place to another. And that possibility seems very salient in the problem that Ben has brought up, which is this arbitrage where the Earth cycles through these energy cycles where renewables are available, not necessarily where they're needed. So I'm curious if you thought about the possibilities of quantum entanglement to teleport energy where it's needed to have less issues with locality of energy.
That would be quite dramatic if it were to be possible. From all we know, entanglement can transport information, not energy. That's what we know of at the moment. One of the reasons, so quantum entanglement is the physics behind quantum computing. And what entanglement then ends up doing is it helps you spread out the information over various quantum states. I don't want to get into the details of quantum physics, but to the best of our knowledge, I don't think entanglement can transport energy as of yet.
Yeah, and I think the issue around geographical load shifting is actually a really interesting question as well that we've thought a little bit about. And so the idea is that if you have lots of renewable energy in, say, Nebraska and a lot less of it in Ireland based on time of day issues, can you move compute from one data center to another? Conditionally, yes. If you decide, maybe Instagram, for example, you replicate your data and then you can serve your feeds from different data centers during different times of the day. That should be possible. The concern is about whether the cost of moving all that data ends up being, again, dwarfing any savings you might get on the computation itself when it gets there. So again, interesting trade-offs with respect to computation and data movement, which is more expensive.
I should also mention, since we are on this point, is that, Ben brought up a really great point about storing energy during off-peak hours in batteries. Batteries are not that environmental friendly at the moment, right? So it's worth thinking about that. Are there alternatives to batteries that are more environment friendly? Because if the batteries are going to be lithium based, I mean, lithium mines can really cause a lot of pollution and destruction, and recycling of batteries is definitely not environmentally friendly. So there is another alternative that I want to put out there, which I don't know how many of you have heard about. It's called pump hydro. Pump hydro is actually a great way to store energy for long periods of time in a very efficient way without much of an environmental havoc. It's basically creating artificial reservoirs of water, the excess energy that you're using to pump water to a higher level or at a height, and at nighttime or at times of where energy demand is much high, you release that water to run the same generators backwards and produce that energy back. So that is something that is being deployed on very large scale instead of giant battery installations in Australia, for instance. And many of the US states are also very conducive to that, especially states that have abundant lakes, streams, and waterfalls.
So I was wondering, given the issue that we're having with computing power reaching a limit with energy production, I wanted to ask, where do you think that nuclear energy plays a role in satisfying that demand for clean energy?
I can take that first. I think nuclear energy has a very central role to play. The conversation in the United States has not been friendly to nuclear energy, and I struggle to wrap my head around it. I think it is nuclear fission is probably our savior out here, at least for the next few decades, or maybe even more, in terms of putting large amounts of carbon-free or near carbon-free energy out there that can sustain our energy needs.
I would agree with that. I think that there's been a lot of excitement about these modular nuclear reactors, these MNRs, and I think that they are exciting. I think the issue primarily is economic rather than technological at this point, because what we're finding is that there isn't a workforce and there isn't institutional knowledge or embedded knowledge where you can essentially build one and then build it again and again and again and sort of amortize the costs of designing and building up that trained workforce, which is why I think the recent efforts to launch smaller nuclear reactors has sort of foundered. I think cost overruns are just not competitive relative to wind, solar, even maybe these massive batteries. So the way I think about nuclear is we're keeping an eye on it, and we compare its costs against the costs of these alternatives financially. I mean,
have a bunch across the back, and we'll just go across.
Thank you. I'm curious, do you think that there should be limits imposed on the amount of energy that these data centers can use? Because otherwise they might just keep growing and growing and growing with no sort of cap, as I think, especially with that energy efficiency paradox.
There was a Nature study and a study out of Lawrence Berkeley National Labs that had looked at the growth in energy consumption for data centers, and it depends. This is where there are lots of numbers and they're sort of inconsistent. The number I think about is that in recent history, there was data center worldwide, energy worldwide, it has been at 1% and has stayed at 1% for a relatively long time. And the reason why we saw clearly we computed a lot more over the last 10 or 15 years, but it's still 1% of the total. And the reason that was, I think, is because we see a lot of inefficient data centers being closed down and moved into Amazon's data centers or Microsoft's data centers, which are run in a super efficient way. So as a result, we saw massive growth in computation At the same time, we saw flat trends as a percentage of the total for energy usage. Now, my caveat there, I think, is that's a one-off, because you can only move everything into the cloud once, and then after that, what do you do? Whether there should be a cap, I don't know. Possibly. I think what you're seeing now with massive data center growth is that most of these companies don't know where things will shake out. So they are just exploring, and they'll eventually hit maximum potential, and then they'll go back and look at efficiency and trimming and everything like that. That goes to the regulation question earlier.
Okay. Hi, thank you so much for speaking. So on the data center topic, I unfortunately don't know that much about it, but I'm wondering how the incentives to decarbonize fit into the business model, as in, and especially with renewables, since there's such a large upfront investment. Are those additional costs passed on to consumers? How do the incentives work for if this would be good for their profitability?
I think there are two types of data centers. I would break it up into the cloud-based data centers like Amazon and Microsoft. So there you have a menu of machines that you rent, and each type of machine that you can rent has an associated price with it. So if these data centers end up spending a lot more to decarbonize their compute, that's an option where you could see the cost being passed on to users of these massive data centers, these Amazon AWS or Microsoft Azure. Internally, the second type of data center are these what are called first-party services. So Meta runs its data centers to serve Facebook and Instagram and WhatsApp and so on, and that happens internally. You're not paying them to access these compute resources. There, the calculus is whether the advertising revenue associated with these services outweigh the costs of trying to decarbonize the underlying infrastructure. And I think that's an interesting question. Right now, they're investing in huge amounts of renewable energy, mainly because those ad revenues are so massive.
Thank you, professors. I wanted to ask, when you talk about the need for a transformative way to do computing, do you think what NVIDIA is doing is a step in the right direction? Of course, CEO Jensen Huang is very fond of talking about how his Grace CPU, Hopper GPU, the whole chip on wafer on substrate, the proprietary high bandwidth interconnect can lead to, as he claims, 12 to 20 times energy efficiency increase over what the same training and inference would take on the Intel-based software. Would such developments be able to avert us from the trend of computing energy consumption overtaking world energy production levels, or is that still part of the same bigger picture?
Yeah, this was partly there on one of the slides I put up. These are what I call as architecture level innovations, right? So architecture level innovations is what NVIDIA has been up to over the past decade and a half, and they do help, especially in data intensive computing. But at the end of the day, neither NVIDIA nor Jensen Huang are going to be able to beat the physics behind the computing. The issue is we are hitting the limits of physics, or will soon hit the limit of the physics. So that's where transformative new ways have to be found, either at materials level, device level, or at the physics level itself. Some people claim quantum is one of those physics, but it remains to be seen what happens to quantum.
I thank you both for this wonderful presentation and all the great work you're doing. This is a question, I guess, of context and offsets. I'd welcome my colleague Shelley Welton to weigh in if she has thoughts about this too. But in terms of the picture that you've painted here about the increasing challenges of providing energy for the AI future and the implications that it has for carbon emissions, I was just struck with the juxtaposition between what you presented, which seems a much more dire picture than what I read this weekend in the New York Times by climate scientist Kate Marvel, who was the lead author of the National Fifth Climate Assessment, which was somewhat optimistic. And I wonder if the trends can you help put into context sort of the trends that we're seeing with computing demanding more energy, with the big picture of energy overall? Are we able to absorb, for example, for some years, the kinds of trends that you've described because of offsetting reductions in energy consumption in transportation, or LED light bulbs, or whatever it might be that we have in other spheres? So that's like a general context about offset in sort of a general way. But you also, Benjamin, mentioned specifically offset programs that these data centers are in, and I wonder how meaningful those programs are, what the evidence might show, if you have any thoughts about whether those are more symbolic gestures, or really can we actually offset our way through? How much of this increased energy demand can be offset? So appreciate any bigger picture outside of the computing context in which to situate the trends that you've identified for us. And it's not to diminish those in any way, but I just wonder how we should think about how much of the larger picture about a transition to a net zero economy is going to buy us some time, for example, to solve the very problems that you've identified here today.
I think computer architects or computer engineers are in a particularly gloomy state of mind nowadays, and the reason that is because we've been relying on transistor scaling trends that have existed since the 1960s with Moore's law, and we have seen that end in the last 5 years. And we have been relying on those trends to get us energy efficient computing. And now that that's ended, we're throwing up our hands and saying, now what? So I think that's probably coloring our perception of the cost of energy and in computing. But I agree. I think there is a very large school of thought that says AI will improve productivity, will improve the efficiency of other ways of working and traveling and so on. And there could be offsets. And those would be really interesting questions to study. And this goes to the question of being able to assess rebound effects. We're trying to understand econometrics now and the methods used to assess and estimate rebound effects in an interesting way, in a robust way. And it's hard because we haven't been able to figure that out yet. On the offsets and the sustainability reports, I think in the near term, the offsets are a meaningful impact on sustainability, because when you look at these sustainability reports, they really emphasize this concept of additionality, which is these wind farms or solar farms might not have been, or were not already existing on the grid. But the question is whether they would have been built had Google not spent this much money, or had Meta not spent that much money on those. So I think that there is a question about that. There is, and to be objective about it, I do feel like there is a perception perhaps that tech companies are rushing in to lock in a lot of the renewable energy for these net zero claims, perhaps at the expense of other consumers of energy in these markets. But there's a lot of renewable energy being installed. In the medium term and in the long term, certainly by 2050, once you get massive penetration of renewable sources, someone is going to have to do demand response. Because you see this in California, where they have much more renewable energy than elsewhere. There are massive hours in the day where they have energy that they could produce, but they can't because they turn it off. The curtailment issue, right? Where you have to turn off your solar panels because there simply aren't enough consumers of that electricity being produced. So if data centers don't do it, someone else is going to have to do it eventually. So I think when we look out to 2050, I think that's the real challenge, getting someone to do demand response.
I'll just add a little context while you guys are thinking of your next question. I think you're totally right. I guess the other piece of the puzzle that's interesting to me is we now have more renewable energy lined up in queues to connect to the US grid than we have on entire energy on the US grid, right? So I think in some ways, like the puzzle going forward is one of like, how do you build a connected system that can facilitate the transformation, right? And this is really a grid policy question. And so, I think the question of exactly what role data centers play in this is a tricky one, but like the more that we are seeing a ramp in the amount of energy demanded out of the grid, the harder this transition becomes, right? So, I think maybe one interesting question for y'all is like, to what extent could data centers be tapping renewables without taxing the grid, right? Like, what is their ability to locate wherever it makes sense instead of, say, like putting it all in Virginia where the grid is feeling stressed? Is there some ability to be smarter about where we're putting data centers to facilitate the larger transition?
I think we have seen a troubling shift in sustainability strategy from big tech recently. I think there was this notion early on that we're going to invest in renewable energy on the grids where our data centers are connected. So there was that sort of coupling between the two. I think for probably financial reasons, these companies are now saying, well, we can build a data center here, but then we're going to build a wind farm elsewhere where they claim that the carbon reductions will be larger than if we were to build yet another data center, another solar farm in Virginia or something like that. So I think there is flexibility in site selection. I think that's largely driven by economics rather than anything else. But increasingly, there are lots of factors that go into data center site selection. Absolutely. Like, for example, there are a lot of data centers in Nebraska now where there's a lot of wind energy, and you can just build much more of it out there. So site selection is an interesting question for certain.
Related to your question that you just asked, I was wondering if there's a conversation about microgrids when it comes to data centers as sort of not straining the current grid, because these are standalone systems that sort of can operate and be resilient whenever there are other disruptions to the grid. And that seems like a pretty feasible solution for data centers. So I was wondering what movements are going on there.
I think early research 10, 15 years ago on using renewable energy for compute did assume that you would install solar panels right next to your data center, and then you would be able to manage your compute based on the availability of solar, maybe sell some of that energy back and so on. I think all of that was interesting, but I think the financial structures or the power purchase agreements that came along sort of took the wind out of that, because now it's easier to go to the utility company and negotiate those contracts, and now you don't have to manage your data center. You don't have to manage the wind farm or the solar farm right next to your data center. So I think the financial aspect of it, or the power purchase agreements, have really smoothed the way for data centers to get more renewable energy. But then again, they're offsets. They're not actually connected to the system itself. So it's an interesting question.
It also goes back to the point that companies like Microsoft are thinking about investing in nuclear energy, because possibly maintaining a modular nuclear reactor is way more economical than installing and maintaining large wind or solar farms next to each other, next to their data centers. It's a more compact form of energy which lasts for a very long time.
Yeah, I'd like to focus on Penn for a second as a case study. It's my informal impression that computing done by students and faculty is increasing at an increasing rate. What's being done at Penn, if anything? What are the long-term concerns about whether that's sustainable?
It's interesting. I see some of my colleagues from the computer science department here, and I think they'll say that the demand, the question has been, how do we get more compute? I think there's been a lot of questions about how do we build data centers to support AI research at Penn and so on. I think that our data centers or our compute is only as efficient as who we outsource our compute to. So typically when Penn buys these very large numbers of machines, they buy space in a third party's facility. And that facility is responsible for power and cooling and so on. So Penn's carbon footprint associated with its compute is only as green as that particular third party's installation. A lot of other faculty at Penn will compute in the cloud with Amazon machines, Amazon AWS machines. And then again, we're only as green as Amazon is at that point.
All right, please join me in thanking both of our wonderful speakers, and thank you all for coming today. Really enjoyed it.